Okay, today we're going to obtain the equilibrium solution to the Liouville equation, and in doing so we'll be able to clearly establish the conditions upon which we can say that a system is at equilibrium. So the first assumption that we'll make is that the system has no time dependencies. So under those conditions, the Liouville equation, we can eliminate the unsteady state term, and we simply have the two remaining terms. So that is the Liouville equation under the first assumption. Now, under equilibrium conditions, we're going to postulate that the solution can be written in a separable fashion. That is, f of n will be composed of two functions. The first one will be a configurational function, and the second one will be a function which depends only on momentum. So we recognize this as a separation of variables postulate, and now all we have to do is substitute this ansatz into the Liouville equation. Okay, now we've substituted our ansatz into the Liouville equation, and for the first term, the momentum space contribution can be taken outside of the derivative argument, and similarly in the second term, the configurational part has been taken outside of the differential with respect to momentum. So now we can see the two terms involving the two new functions, h sub n, which is only a function of momentum, and n sub n, which is only a function of the configuration of the system. Also note that we've assumed that the force here is only a function of position, and it has also been taken outside of the argument of the derivative with respect to momentum. Our second assumption is that there will be no dependence on the choice of the locator molecule K. And this is inherent in a system where there are no spatial variations. That means whatever each of the kth terms are, let's take for example k equal to 1, the net result of these two terms for k equal to 1 would be the same as if k was equal to 2, because now k equal to 2 locates the position of any molecule at some other point in the system. Again, this is our lab frame. So if there are no spatial variations in the system, we wouldn't expect any differences in the summation of these two terms for different values of k. What this means is that if the sum of all the k terms is 0, and each of the k terms is the same, that means then that each of the k terms must be equal to 0. Okay, so assumption 2 now is that there are no spatial variations in the system, so each of the k terms must be equal to 0. So we've written that out here, one of the k terms. And now we can divide through that equation by the product h sub n to n sub n to obtain an equation that looks like And now we're starting to see something that looks familiar to us, where we're starting to see a separation in the momentum part and the position part, and now we have to reckon with the coefficients and how we're going to rearrange this equation to get a separation of variables type solution. Okay, our next assumption is going to be that the system is isotropic, which means that there's no preferred direction. And under those conditions, again, each of the terms in every direction, so we have, for example, P, the first term, that would be equal to, in component form, say pk1 over m, n sub n. And now this is simply a product of the x direction, and then the second term would be the y direction, which we could call pk2. And then finally the z direction, which we could call pk3. So taking the regular dot product and this Cartesian coordinate system would result in these three terms. If the system is isotropic, then here's the locator vector to this molecule, and it has each of the three components that we could identify. And if there's no preferred direction, then the contribution of each of these terms should be the same. There shouldn't be any bias with respect to x, or with respect to y, or with respect to z. So we would expect the component forms to be identical. So again, it's a situation where if the sum of the terms is equal to 0 and each of the terms is identical, then each of the terms must by themselves be equal to 0. Okay, so under the third assumption that the system is isotropic, here is the one component of that equation, and we've used a subscript L here and to indicate the three directions, so L could be 1, 2, or 3. And now this equation is simply a scalar equation involving the components in one particular direction. So we can now divide through by the product PKL FKL and obtain a separable equation and we'll move the mass to the other side. So now we've just simply divided through both equations by the product PKL FKL, and we've moved the momentum term now to the right hand side of this equation, and we've also moved the mass over to the right hand side, and we've obtained this equation where now the first term here only depends on positions, and the second term only depends on momentum. So the only way, of course, these two could be equal to each other, since one is a function only of position, one's a function only of momentum, is that if they're both equal to a constant, lambda, which is called a separation constant.